Okay, class, we're going to take a look at solving trigonometric equations. In this first example, we want to decide whether the angle theta equals pi over 4 is the solution to this equation. 2 times the sine of theta. So I'm going to substitute pi over 4 for theta. Minus 1 equals 0. Okay, the sine of pi over 4 is the square root of 2 over 2, so that's like taking 2 times the square root of 2 over 2, subtracting 1, do I get 0? Okay, I can see I will not get 0 because square root of 2 minus 1 does not equal 0, so no for pi over 4. Let's try the other one here, pi over 6. Okay, so substituting the sine of the pi over 6, which is 1/2, you get 2 times 1/2. Okay, that works. Okay, but not only is pi over 6 a solution, we also can go further along here to the angle 5 pi over 6, which has also got a sine of 1/2. So is 5 pi over 6. Okay, so now let's look at another pretty simple equation, but we want to find a way to describe every solution for the equation. So if we have, for instance, cosine of theta equals 1/2, then let's find as many solutions as we can to begin with. So where is the cosine 1/2? So at pi over 3, okay, we got our 1/2, and anywhere else we got, yeah, we got it again over here at 5 pi over 3. Okay, so there's two solutions available to us on the unit circle, but there's an infinite number of solutions if you think about all the coterminal angles of pi over 3. So for instance, if I take pi over 3 and I add a full rotation to pi, I'm right back there at pi over 3. I'm going to have the same cosine. So we also know if I write this as pi over 3 plus 6 pi over 3, I can see that 7 pi over 3. I can also see that if I take pi over 3 minus 2 pi, so I'm going to get negative 5 pi over 3. Just all sorts of solutions here. Also, if I start at 5 pi over 3 and I add a 2 pi, okay, so I'm going to get a 11 pi over 3, and so on. So we want a generic way to say this is if we let k be an integer, then our theta, our angle that we found, plus 2 times k times pi, and the other base that we found, plus 2 times k times pi. These are all going to be solutions. Okay, so k is just telling us how many times to go full circle back to that place. So if k is 0, then I don't add anything to the base solutions that I found within the unit circle. If I let k be negative 1, then I'm going to rotate clockwise back to the very same terminal side. And if k is positive 1, I'm going to rotate counterclockwise back to the terminal side. So this k just tells how many times we're going to go around the circle in one direction or the other. And there's an infinite number of coterminal solutions. Okay, so let's take that idea and solve another equation. In this case, they're going to go ahead and tell us to limit our solutions for angles between 0 and 2 pi because we could create an infinite number of solutions. So let's take this equation 2 sine theta plus the square root of 3 equals 0. Alright, so we want to isolate this sine theta so we can determine the angle that makes that particular sine. So we have 2 sine theta equals negative square root of 3, and of course we'll divide both sides by 2. So we know that the sine of theta equals a negative square root of 3 over 2. Alright, so we're only interested in anything that's on the unit circle, one rotation of the unit circle, and so we see that 4 pi over 3 has a sine of negative square root of 3 over 2. So theta equal 4 pi over 3 is one solution. And then I go over here to 5 pi over 3 where I also get a negative square root of 3 over 2. So theta is also equal to 5 pi over 3. Okay, and the only other solutions I would have to cycle some multiple of 2 pi, and that's going to take us beyond the scope of our solution set. Okay, for this next example, we're going to take a look at solving the sine of 2 theta equals 1/2. This is a little trickier because we're using a double angle. We call that a double angle because we're doubling it before we're asking for the solution. So we've got this modification on the inside, and what we can tell from this is that 2 times theta is equal to pi over 6, and another place where we have a half is going to be over here at 5 pi over 6. Okay, and now we have to take into account that there are many angles on the period of 2 pi. So what we really mean is that 2 times theta is equal to pi over 6 plus 2 pi times k for some integer k. And we're interested not what 2 times theta is, but what theta is, so we're going to divide everywhere by 2. Okay, so it's going to be so in terms of theta, we're going to get one situation where pi over 12 plus k pi. Okay, so reducing everywhere by 1/2. And over on this side, we have 2 theta equals 5 pi over 6 plus 2 pi times any integer. And the same thing here, we're going to reduce. So the other case is where theta is equal to 5 pi over 12 plus some integer times pi. Okay, and if we go through a sequence here where we allow k to equal, say, -1, and then we're going to take pi over 12 minus pi, the result of that would be -11 pi over 12. For the 5 pi over 12, if we take 5 pi over 12, k is -1, so we'll get a minus pi. and that ends up being negative 7 pi over 12. Okay, notice that we're only interested in answers in this interval, so these two are not going to matter. Let's move on to the 0 for k. Okay, if we put a 0 in for k, then we're just going to get the pi over 12. And we're just going to get the 5 pi over 12 plus 0 times pi. So, okay, these were both of our original answers once we solved for theta, and they are both in between 0 and 2 pi. So we're going to keep these. We're not using these because they're not in our interval. When I let k equal 1, we're going to get pi over 12 plus 1 pi. And if I add that, I get 13 pi over 12. That's a keeper because it's between 0 inclusive and 2 pi when k is equal to 1. Okay, so keep that. Over on this side, when k is equal to 1, we get 5 pi over 12 plus pi. And that's going to equal 17 pi over 12. Okay, and that is also within 0 and 2 pi, so we're going to keep that. Now let's bump k up to 2. So if I take pi over 12 and I add 2 pi, full rotation, and that's going to be 25 pi over 12. That exceeds 2 pi, right? 12 goes into 24 twice, and then we got 1/12 more. So that's beyond our scope. Let's try 5 pi over 12 plus 2 pi. That's going to be even bigger at 29 pi over 12. Okay, so we know that we can stop with the k here of between 0 and 1, but it generates 4 solutions instead of just 2. If we have a double angle here, we create room for more solutions instead of just the 2. If that were just theta, we would have only found 2 solutions, but by creating a double angle here, we've generated more solutions that are within 1 rotation. Okay, so our solution set pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12.